Hello. I think we're finally there. All right. Let's see here. Just trying to get things set up here. I was having a hard time getting connected for some reason. Just trying to get things set up here. Hard time getting connected for some reason. Yeah, it looks in focus. And the limits of my board. Focus. All right, I guess I can get started now. Just get the audio turned off here. I don't know if anyone's really joining me here today, but I will try to look into the chat periodically. Today, I'm not going to get through everything I had listed on the Hangout itinerary. Something's come up where I have to leave in a little bit. But and today, what I'm going to do is I'm going to talk about the antenna used in the radar ranging the distance to the sun, and talk a little bit about matter, mass, weight, density, acceleration, and some of the ongoing tests that I'm doing for future videos in Hangouts. And I'll take a break here to check to see if I do need to go. Something's come up or someone needs my help here in about an hour, and I'll check and see how that's going. Whether or not I really do need to disappear. So here we are, Hangout number 2. My name is George Notchik, and a couple weeks ago I did a Hangout where I discussed the radar ranging the distance to the sun and how it was done. And since then, I've had some questions regarding the antenna that was used and some other issues, and I'm just going to go through that right now to add a little more detail in how the antenna system was set up and whether or not movement of the Earth was really going to affect the results. It's actually pretty interesting how this was all set up. Now, in the experiment that was done, or the test that was done in 1959 by a group associated with Stanford University. They had the use of an antenna system that was being used for some other experiments. And so they just kind of piggybacked off that effort, because to install the type of antenna range that was required for sending pulses to the sun and looking for the echo returns, as you have with radar, it is quite a logistical effort. And they had the use of this antenna system, and with some minor modifications was able to use it. Now, the frequency that was determined that would be optimum for sending pulses to the sun and not have them absorbed in the corona was 25.6 megahertz. This was done through an analysis of looking at plasmas. And so it was determined to use a relatively low frequency of 25.6 megahertz. That's right, right a little bit below the citizens band radio here in the US, close to being, it's about 11.7 meters in wavelength. And the hams have the 10-meter band at 28 megahertz. So it's right in that region, 11-meter band, 10-meter band. It's a relatively low frequency for doing these types of things. So your antenna has to be physically large in order to get any reasonable gains that they were looking to get with this type of an antenna system. And keeping in mind, this was shortly, not long after World War II having ended in 1945, 14 years later. An antenna used in that period of time for getting reasonable gains in bandwidth is what's called a rhombic antenna, as in a rhombus. Oops. A rhombic antenna. And as the name suggests, it's a wire antenna in the form of a rhombus. About that time, a new type of antenna was being developed called the log periodic, and the rhombic antenna has fallen out of disfavor because the log periodic antenna has a much wider bandwidth and isn't as physically large as a rhombic antenna. But back in this time, they decided to use an array of rhombic antennas. And what a rhombic antenna is you physically mount this on poles with wires in the shape of a rhombus. Kind of like this. Yeah, redraw that. And you have poles that you stretch these wires between. And this antenna is physically large. Typically, each of these legs tends to be on the order of a couple wavelengths or longer for the signal that you're using. And by using the correct vertex angles on here, you can get the lobes of the antenna pattern for each one of these legs to start lining up. Basically, what happens is this, is you have a feed point at one of the acute angle vertexes, and at the far end, you load it with a non-inductive resistor. And what happens when you do that, each one of these legs has a little antenna pattern that basically looks like this. You have some side lobes and you have two main lobes. And the same thing happens here. You have a couple side lobes, you have a main lobe, two main lobes, you have a side lobe here, two main lobes, and two main lobes here. And what you can see with the proper selection of the angles, you can get one of the main lobes of each one of the legs to line up. That lobe, that lobe, that lobe, and that lobe line up, and they reinforce one another. And the radiation from each one of these lobes add and reinforce one another, and you end up with an overall antenna pattern that looks something like this. And what this means is that if you had an isotropic radiator or an omnidirectional radiator, it would radiate equally in all directions in a sphere. But with a directional antenna, a unidirectional antenna, what you try to do is concentrate the energy in one particular direction. And this basically tells us how the energy is concentrated. Is off to the sides, you have very weak reception. And the back, you have hardly anything. There might be some real small little lobes. The longer the distance out from the feed point, the more intense the signal is. So going directly in line off the end of a rhombic antenna, you have maximum gain. And that's where your maximum gain is. This is a pattern looking down. We're looking down, say, the whiteboard is the surface of the Earth, and we're looking down from above at the rhombic antenna. The antenna is parallel with the surface of the Earth, and we're looking at the radiation pattern. Now, in an elevation angle, if you're to look on the side, say, here's the surface of the Earth, the rhombic antenna is stretched between two poles, and you'll end up with a shallow radiation skyward. It doesn't shoot direct off the end. All antennas tend to have an elevated angle of radiation. So you can think of this as being a rotated solid. We're just looking at a cross section, but the radiation pattern is actually three-dimensional. So you spin it around its axis and then tilt the axis upward about 5-10 degrees or so. That depends how much of an elevation angle you get, depends upon how high above the Earth in terms of wavelengths you mount this rhombic antenna array above the Earth, influences this skyward shoot of your main lobe. So there's things that influence it. The amount of directivity, or how narrow this beam is across, whether it's going to be a few degrees or 10 degrees, depends upon how big of an array you make, how many wavelengths each one of these legs tend to be. Well, in this particular test, what they did was they built a broadside array of 4 of these. So let's look at that. So we take 4 of these rhombic antennas and mount them side by side. We're looking down to the surface of the Earth. The whiteboard is the surface of the Earth. Here's our rhombic antennas. They're mounted broadside. And to get each of the patterns to reinforce one another is what you do is you hook delay lines by a simple delay line for a given frequency is you just choose the proper length of feed lines and you put them into a combiner. And each one of these lengths, L1, L2, L3, L4, will be maybe a little bit different by certain lengths. And the reason for that is you want, if the signal is feeding array number 4 or antenna number 4, you need to put the phasing a little bit different in antennas 2, 3, and 1 so that the radiation patterns tend to be in phase and reinforce one another. This is called what we call a phased array. And what's really nice about something like this is we're only operating on one particular frequency, 26 or 25.6 megahertz. So the antennas can remain fixed. The delay lines are very simple. They're just appropriate lengths of transmission line, because the phasing changes according to the length on the line and the propagation velocity as to when the signals arrive at each one of these antennas. So this ends up being very nice when you are using a fixed frequency, because you don't have to adjust these because everything remains fixed for the 25.6 megahertz. Then once it goes into the combiner, this thing goes into what we call a TR switch, transmit receive. And on one side of the switch, you have your transmitter. And on the other side of the switch, you have your receiver. And this just happens to be a switch that either connects there or connects there. So what you first do is you connect to the transmitter, you send your pulses out for about 900 seconds, these pulse trains, and then after 900 seconds, you switch the antenna array to the receiver, you shut the transmitter down, and you listen for the return echoes. Now, with a rhombic antenna, you can change its characteristics by what you do at the end. If you put a resistive load at the ends of all these, it tends to make the antenna more directional and gives you just one main lobe. If you leave it open, it becomes bidirectional. You receive equally going out the front as you do out the back. And you typically feed the antenna, these rhombic antennas, at one of the acute angles on the rhombus. And then the other end, again, you terminate in a resistor or you leave it open depending upon what you want the characteristics to be. Now, you can also improve the efficiency of this antenna upwards to 70 to 80% and get more gain by replacing these resistive terminations by what we call an open stub. An open stub is just a piece of transmission line that's open, and depending upon the wavelength, if you open or short a piece of transmission line, let's say you choose a quarter wavelength for its overall length. If it's open on this end at a quarter wavelength down the line, it looks like a short. And if you short this end of the line, it looks like an open on this end of the line. And with something in between going a quarter wavelength, the line will either look inductive or it will look capacitive. And it's lossless. An ideal inductor and an ideal capacitor are lossless. They don't absorb any energy. So if you have these open stubs on the end, they don't dissipate any power. And what they'll do is they'll reflect signal back into the line, and with the proper choice, the signal that's reflected back into the antenna can reinforce the signal coming from the transmitter and give you more efficiency and more gain. So that's what you can do here with the rhombic antenna. Now, the radiation of a rhombic antenna, like I said, it has some angle with respect to the Earth, and this angle can be made really quite shallow and almost parallel to the Earth, or a very small angle above the Earth. And that depends upon the operating frequency and the physical construction of the antennas. Now, in this sort of antenna array where you have 4 rhombic antennas, it takes quite a bit of area to build up an array like this. In this particular test that was done, this array took up an area of 800 feet by 725 feet. So in this direction, it was 725 feet. In this direction, it was 800 feet. A lot of area. When you look at that, then this is telling us that a rhombic antenna going from end to end was about with the operating frequency of 25.6 megahertz, a wavelength at that frequency is 11.7 meters. So going from end to end, that's about 19 wavelengths at that frequency, a very large antenna. But that gives you more gain. The larger the antenna is in terms of the wavelength of the operating frequency, the more gain you get. I built something like this when I was a teenager for picking up an AM signal. We had a lot of property, and I strung and made a rhombic antenna between trees that took up over a 1/4 mile because I wanted to pick up some AM signals in the broadcast band. And it really worked quite effectively. But the downside of it is with an antenna array like this, where you have poles in the ground, you string the wires between, you can't rotate it. You can't move your antenna pad around. You have to have it aimed at the place, at the station that you want to pick up, because you just have no hope of ever rotating or reorienting the antenna because of its sheer physical size. Now, you can imagine with this antenna that they were using, it turns out that they only had a window of opportunity around the equinox, around the around the equinox, the equinoctial period, and they were conducting this test between April 7th, 10th, and 12th of 1959. And the reason for that is that the sun appears in the main lobe of the antenna system only during this period, near the equinox, because of where the antenna was oriented on the Stanford property. So they only had a couple weeks of a window of opportunity in which to do this, because you can imagine between how the antenna is aimed and its elevation of the radiation pattern, the sun is only going to be in view of the main lobe for a certain period of the day. It turns out that it was only, as the sun's passing by, it is only in view of the main lobe of the antenna for 30 minutes, and over a period of about a week or two in the year. So they had to really get their act together and get this thing done during this couple-week period, because you can imagine, you know, as we get closer to summer, the sun gets higher and higher in the sky as it passes by, and it will miss this main lobe if you wait too long in the spring, or it'll be too low if you try to do it any sooner than the equinox, where they had, as they had this antenna set up. And then again, on any one of these days, they only had 30 minutes over which the sun would travel through the lobe, through the main lobe, for them to transmit and receive the signal. So that's basically what was done here with this particular test. Now, let's look a little more about the orientation of the Earth with respect to sun during the test, because some people seem to think that somehow the movement of the Earth would make it impossible to send a signal out and receive it back. And that's not the case. That's not true at all. And we'll go through that here in a second. I'll go through the numbers and show you why it is entirely possible to do this without worrying about the movement of the Earth. Now, let's look at the Earth as it's orbiting about the sun. Here we have the sun, and the Earth is in its orbit about the sun. The distance from the Earth to the sun is 1 astronomical unit. 1 astronomical unit is 149,597,870,700 meters. That's the exact definition of 1 astronomical unit, which is approximately, the number I use is 149.6 times 10 to the 6 kilometers. Okay, this is 149 billion meters, and a kilometer is 1,000 meters, so it's 149.6 million kilometers, which works out to 92.96 million miles, or 93 million miles. Now, the Earth in its orbit about the sun, the Earth, its tangential orbital velocity, the velocity of the Earth, is 30 kilometers per second, which is 18.6 miles per second in English units. Now, the travel time for an electromagnetic wave to be sent out from the Earth to hit the sun and be reflected back is about 1,000 seconds. Its trip from the Earth to the sun each way is 500 seconds. And that's really quite accurate, because if you look at the speed of an electromagnetic wave in a vacuum as it's traveling from the Earth to the sun, is 299,792,458 meters per second. That's the velocity of light. This is exact. This is the exact velocity of light in a vacuum. And the number I use is 299.8 million meters per second. Now, if we take the distance that the signal travels from Earth to the sun and divide by its speed, which is the speed of light, we get the time that it takes. So 1 astronomical unit divided by the speed of light. If I take this number, divide by this number, we get 499.005 seconds. So it's very close to 500 seconds on a trip from the Earth to the sun, and 1,000 seconds adding another 500 on the return trip. It's basically within 2 seconds of 1,000 seconds. It's actually 998 seconds. So 2 seconds out of 1,000, that's 0.2%. So that's negligible to worry about. So the question we have to ask ourselves is, how much does the Earth move during this travel time of the signal, this pulse train going to the sun and returning back to the Earth in 1,000 seconds? Well, we know the velocity of the Earth is 30 kilometers per second. So all we have to do is multiply by the time. So if we take the velocity of the Earth, which is 30 kilometers per second, and multiply by 1,000 seconds, we get 30,000 kilometers, or 30,000 kilometers is how far the Earth travels in that time. So from this position to this position, the Earth will have traveled 30,000 kilometers. Well, let's look at that in terms of Earth diameters. Well, we know that the Earth has a radius of 6,371 kilometers. So the diameter of the Earth is twice that, which is 12,000, let's say 12,700, or 12.7 times 10 to the third kilometers. We're just doubling that number. Well, this distance, I'll call the distance that the Earth travels in 1,000 seconds. Let's call that SE. So the let's ratio SE to the diameter of the Earth. Well, SE is 30. Let's see what I do. Yeah, SE is 30,000 kilometers. So this is 30 times 10 to the third kilometers. And we're going to divide that by the diameter of the Earth, which is 12.7 times 10 to the third kilometers. And this comes out to 2.35. So in that 1,000 seconds, the Earth has only traveled less than 2.5 diameters. Well, on this rhombic antenna, it has a beam width on the order of degrees. So the rhombic antenna is basically, say, looking over this sort of an angle. So it's very easy for the antenna array to pick up a signal being returned from the sun, because the Earth hardly moves at all. A better way to look at this, of course, is in terms of angular measure. Let's look at that. Okay, now we have the sun, we have the Earth in its orbit about the sun. This is 1 astronomical unit. Now, how far does the Earth move in this 1,000 seconds? It's going to move a distance SE, which is 30,000 kilometers. How much is that in angular measure with respect to the sun? Let's call this angle theta. Well, angle theta is just the ratio of the distance that the Earth has traveled to the distance to the sun, which is 1 astronomical unit. So theta in radians will just be SE over 1 astronomical unit, or 30 thousand kilometers over 149.6 million kilometers. And this works out to, if you perform that division, you get 0.30002005 radians. This, in angular measure, is 0.1 or 0.0115 degrees. Or in terms of arc seconds, this is 41.4 arc seconds. Now, this works out to, this is 1/44th the angular diameter of the sun or the moon. We see the sun and the moon in the sky at about an angular diameter of about 1/2 degree. So the Earth moves with respect to the sun less than the angular diameter, 1/44th of the angular diameter, just a sliver. If the moon were the Earth and we're the sun looking at the Earth, the moon would only move 1/44th of its angular diameter, very slightly. And that's what we would see. And that's what we have with the Earth as it moves about the sun. There's hardly any movement whatsoever. Keep in mind that the beam width of this rhombic antenna is on the order of degrees, and the Earth is moved less than 1/44th or close to an 80th, 1/88th of a degree. So with the antenna pattern, if the lobe, say, was even as low as 1 degree across a beam width, the amount that the signal has moved or the Earth has moved is less than close to 1/100th of that. So there's absolutely no problem whatsoever of receiving a signal that's being reflected back from the sun, even though it takes 500 seconds to propagate from the sun to the Earth. There's the movement of the Earth is inconsequential. It's just not going to matter at all. So hopefully that explains the antenna system and the array used in this test for ranging the distance to the sun. I'll look now in the chat and see if there's anyone there. If anybody has any questions, I'm looking at the chat. Oh, hi, Rhombus. If there's any questions, is there anything else that I haven't covered about the antenna array and the rhombus and stuff that maybe you'd like to have me go over? Gosh, it's got to be pretty late there for you, Rhombus. Let's see, it's after 1 o'clock there. Yeah, you better go to bed. So let's see. I'm just going to take a short break here. Excuse me. Get a drink, and then I'll talk about mass inertia and densities and accelerations a little more. I covered it last time, but I'm going to recap that and try to hit it home a little more here today. Oh, as far as how the antenna, the size of the antenna impacts the radiation pattern, I'm not going into that. That's really quite technical. You have to go into Maxwell's equations, boundary conditions, and all that, and antenna theory to find the relationship between the size of the antenna in terms of wavelength of the signal being propagated in comparison to the size of the antenna. But a good rule of thumb is it always works out, regardless of the size of the antenna or the type of antenna, whether it's a rhombic, a Yagi-Uda antenna, or a parabolic dish, is the bigger the antenna in terms of wavelengths, it's the number of wavelengths that's important. And the more wavelengths that you have, the greater the physical size of the antenna, the bigger the capture area, the bigger the aperture of the antenna that we call it. And hence you get more directivity and more gain because of just having a larger aperture area in which to capture the signal being received. So, like if you look at these large dish antennas used for radio astronomy or for space communication, like with the Voyager spacecraft or the Mars rover, they're typically using 70-meter antennas. One in Spain, there's one in Spain and one in, I think it's Australia. And at the frequencies of operation, on space communication, like to the Mars rover and the Voyager spacecraft, the frequencies are anywhere from about 4 or 5 gigahertz up to around 8 gigahertz or so. So the wavelength on a 1 gigahertz signal, remember that the speed of light we designate with the symbol C. Let's see here, I gotta. If we look at the relationship, the wavelength, which is in meters, this is a length. This will be the speed of light in meters per second times the frequency, which we use either nu or F. I'll use F because it's more indicative frequency. F stands for frequency. Frequency is cycles per second, meters per second. So meters per second times, I'm sorry. Oh gosh, this has got to be divided by F. C divided by F. Jesus, this stuff affects me. This is meters per second. This is 1 over second. So this ratio comes out to meters, or lambda F. This is meters. This is 1 over second. So this is a velocity or the speed of light. That's a relationship. So keep in mind, like speed of light is 149.6 kilometers per second, or million kilometers per second. Let's put it in terms of meters. Times 10 to the 9th meters per second. And if we divide by, or no, that's not the speed of light, that's astronomical unit I'm going with. Speed of light is roughly 299.8 meters per second. That's the speed of light. This is C from what we had before. And if the frequency, say, is 1 gigahertz, or let's just say 10 gigahertz, so this, a gigahertz is 10 to the 9th hertz. So this is 10 to the 10th hertz. So the wavelength of a 10 gigahertz signal, if we look at, is we have let's just say this is 300. This is million. This should be 10 to the 6. 300 million meters per second. And we divide by 10 to the 10th hertz. So we see then that lambda, or the wavelength of a 10 gigahertz signal, this is 6, 7, 8, 9, so 0.03 times 10 to the 10th meters per second, divided by 10 to the 10th. So we have 0.03 meters, or this is 3 centimeters. A 10 gigahertz signal has a wavelength of 3 centimeters, very short. So if you're running this thing through a parabolic dish antenna that's 70 meters across, you can see that a 3 centimeter signal, wavelength of 3 centimeters, this is an awful lot of wavelengths. So 70 meters or 7,000 centimeters divided by 3 centimeters gives us close to 2,000 wavelengths, 2,300 wavelengths. So you can get an awful lot of gain out of a dish antenna that's 70 meters across when you're operating at, say, 10 gigahertz, or even at a gigahertz, having it being as much as a gigahertz. It's a large number of wavelengths across that dish, so it has an awful lot of gain. So basically, you look at the size of an antenna with respect to the wavelength of the signal that you're using. So the bigger the antenna is in terms of wavelengths, the more gain, more directivity of the antenna in general. That's true of all antennas. So I'll look at the chat here again. Hey there, Kaiser. Oh, I see you caught my error. Yeah. You know, sometimes I get ahead of myself. So before I get away from this subject, does anyone have any other questions regarding the radar ranging to the sun to find the distance to the sun? Yeah, sometimes I try to get a few steps ahead of myself, Kaiser, and that I'm thinking ahead and my hand isn't following. So I do know the correct value for the speed of light, though I might not write it down. Let's see, I'm trying to think of are you going to be around for a bit there, Kaiser? I could let's see here. Shoot, I didn't want to do that. Okay, I'm just going to take a quick break here, and then talk a little bit about mass and inertia again. So I'll just write here so you know that I'm still here. I'll be back in about 2 minutes. I need to fill up my cup. So it's getting a little dry. Yeah, well, it's pretty late for Rhombus. That's why he's gone. It's 1:30 in the morning there. Yeah, it's cooling off here, Kaiser, but it's still holding its own. It's around mid-40s on the Fahrenheit scale here yet. We typically won't have the ground cold enough for snow to stay around. Generally, that occurs right around Thanksgiving time. So we're about a month away before we'll have snow sticking on the ground. We've had a few snows, but they just don't last. And it'll be about mid-December, right around mid-December when we get first ice on the lake. It takes quite a while for the lake to cool down enough for surface ice to form. Because in about a few weeks, what we get in the lake, there's a phenomena called turnover. It's really quite interesting. Is that as the surface water cools, cooler water is denser, so it settles down to the bottom of the lake. But there comes a point when the surface water, you have a layering occurring, and you get a dense layer of water on top of the surface water, and then all of a sudden, it just all drops. and the warm water comes up to the top. It's an interesting thing. Is you would think that as the surface water cools, that the cooler water just continually, in a continuous manner, drops down. But actually, that's not the case. You get a layering that occurs, and you can get some cooler, dense water actually floating on top of the warmer water underneath, and then all of a sudden the whole damn thing just drops down, and the warm water comes up, and we call this turnover, and you see it on the surface of the lake. I'm hoping I can capture it this year. It generally occurs over a period of hours, and you just never know when it's going to occur, whether it's going to be late at night or in the afternoon or the morning. And I'm hoping I can catch it. I saw it one time about 10 years ago. It was really interesting. Is the whole lake, the bay out here looks like waves, but they're stationary waves. They don't go anywhere. You'll have a whole series. If you look on the lake, you have a whole series of these waves, looking down the waves, but they don't move. They just sit there. It's like a water fountain. Like the water is coming up and overshooting the surface. So you get these mounds of water that are coming up. And they're stationary waves. It's really, really quite interesting. That happens during what we call turnover on the lake. And that should be happening in the next 2 or 3 weeks. And I'm certainly thinking I could catch it. It'd be an interesting thing to get on film and show people what happens. Okay. Now, let's talk about, I talked about this last time, but it seems I need to hit it home a little more. Mass. What is mass? Mass is the amount of physical matter contained in an object. It's a measure of the amount of matter in an object. The units in the MKS system, meter, kilogram, second system, is the kilogram and the gram. In the English units, mass is measured in what's called slugs. It's not very often used. The unit of mass in the English system has fallen out of disfavor. People really don't use it much. But mass is responsible for an object's inertia. Inertia is the tendency for a material object or body to resist changes to its position or motion. If a body is in motion and it has a lot of inertia, it's difficult to stop that body from moving. And likewise, if a body has a lot of inertia, it's hard to push to get it going. You can think of like a rowboat sitting in water. We all know, like if you had a block of wood or whatever that doesn't have a lot of mass, you can give it a shove and it easily moves. Now, if you happen to have a big cruise ship sitting there, it's still in the same water, still has the same ease of movement in terms of friction on the hull as a little block of wood, but you can't give it a shove and get it going. It's because of its inertia and the tremendous amount of mass in that ship. Mass and inertia are often used interchangeably to describe this property of matter. Mass has units in science. Inertia does not have any units. It's more of a concept or thought of as a property of matter that results from the mass, but that's not entirely true. We can talk about mass as a result of an object's inertia or the other way around. It's kind of nebulous, but mass and inertia are a property of matter that gives matter or an object the tendency to resist changes in its motion and position. The more inertia or more mass an object has, the harder it is to change its position or stop its motion. Now, the concentration of mass or matter in a given volume, we call it density. The density is a concentration of matter in a given volume, and we generally give it the symbol rho. Rho just happens to be the ratio of the amount of mass in the volume of an object. So the units, mass is kilograms, volume is cubic meters. So kilograms per cubic meter. This is a rather large unit. A lot of times we use grams per cubic centimeter, and a cubic centimeter is many times, like in medical profession, chemistry and stuff, called cc's. That stands for cubic centimeters. So a cc is just 1 cubic centimeter, or it's grams per milliliter. 1 milliliter, or 1/1000th of a liter, is a cubic centimeter. They're interchangeable. The volume of 1 milliliter is the same as the volume of a cube 1 centimeter on a side. So 1 cubic centimeter, 1 cc, or 1 milliliter. So these are the units of density. Density is a figure of merit in a sense. It tells us how compact an object is. The more dense an object is, the more concentrated the matter is in a given volume. So that's all density is. It is a figure of merit that basically tells us the compactness or how matter is concentrated in a volume. The densest material, natural known material on Earth, is osmium, the element osmium. Gold is very close to it, and so is tungsten, very close to the density of osmium. Now, how about acceleration? Acceleration is just the rate of change of velocity, delta v, delta mean a change in time. If we could say that this is the final velocity minus the initial velocity over final time divided by initial time. That is, if you have an object that's moving, you measure its initial velocity, you measure its final velocity, and you take that interval of time between those two measurements, ratio them, that gives you the average acceleration of an object. Now, this can be very deceiving. This is for average acceleration. I'll call it A average, because you could say, let's say we plot velocity with time. Here we have our initial velocity, and it could change over time, but if it ends up being the same value at, say, T2 as it was at T1, this calculation would give you an average velocity of 0. However, instantaneously, the velocity is the slope of this curve. It's the change in velocity over the change in time. So the instantaneous velocity is changing with time, but the average velocity over an interval period may be 0. It could be the same value as the instantaneous velocity or acceleration at some point. So you have to be careful on the time interval that you choose for computing your acceleration. But all acceleration is it tells us how velocity changes with time in an object's movement. That is, if an object is moving and its velocity doesn't change, if the velocity is constant over all time, then there's no change in velocity. So delta V goes to 0. So the acceleration goes to 0 when the velocity is constant. That is, it remains a constant value, say at 7 kilometers per second, going in a straight line. It has no acceleration because it's maintaining a constant velocity. Any object moving at a constant speed has no acceleration. Acceleration causes velocities to change, or the direction of an object to change. So all acceleration is it's telling us the rate at which an object is changing its velocity. For example, if you have an object that's you're on top of a tall building and you have a ball and you hang over the edge of the building and you let the ball drop from 0 velocity. This is our ball. So the initial velocity is 0. You're holding it and then you release it. It's going to drop. And the rate at which it drops, its velocity changes with time because of gravitational acceleration. The velocity of an object is the gravitational acceleration times the time. So at t equals 0, it has 0 velocity, but say it takes 4 seconds for the object to hit the ground from when you release it. So if t equals 4 seconds, we know that g is 9.8066 meters per second squared. So we can compute the final velocity. The final velocity will just be g times the time that it takes to hit the ground. In this case, it's 4 seconds. So 4 times 9.8, 4, 9, 30, so it'd be about 39.2 meters per second is the velocity at which it will hit the ground. Now at 2 seconds, say if we're here at 2 seconds, halfway down, well that won't, then at 2 seconds, the velocity here is going to be just 2 times 9.8, or 19.6 meters per second. So if you release an object and let it fall, its velocity will increase linearly with time. Double the time, the velocity doubles. Have 1/4 of the time, it has 1/4 the velocity at which it would have, say, at the time that it takes to hit the ground. So it's a linear rate of change. We could plot it, velocity versus time. We start out at time equals 0, the velocity is 0, and it just increases in a straight line. And the slope of that line is just 1 over little g, 1 to little g, or 9.8 meters per second squared. That's the slope of that line. So the velocity increases linearly with time as the object is falling. So that's what acceleration is. It just tells us the rate at which an object changes its velocity. But of course, we have to keep in mind in general, for say curvilinear motion, you could have constant magnitude of velocity with a direction change, because these quantities, velocity and acceleration, they have not only a magnitude associated with them, they also have a direction. So what we would have is, in general, velocity is a vector, and it has some magnitude v. This would be a scalar. I'm designating a vector by a bar over it, and there would be a unit vector associated with that, giving its direction. I'll just call it a sub r. This is a unit vector, has unit magnitude. That's how we designate velocity. The magnitude of the velocity vector is just v. Because if I look at it mathematically, we have the magnitude of v, a sub r, and this would be the magnitude of v times the magnitude of a sub r. But this is a unit vector, meaning that its magnitude is 1. So we end up with the magnitude of v, which is just v, a positive number, which is a scalar. Now, acceleration is also a vector. It also has a magnitude and a direction associated with it. Mathematically, acceleration, instantaneous acceleration, is the limit as time goes to 0, is you shrink your time interval down, of delta v over delta t, where delta v is your velocity vector. Well, this in mathematics is called the derivative. This, to write it in terms of calculus, this is the derivative of the velocity vector with respect to time. And when you take the derivative or changes in a vector, this is v times the derivative of the position vector, a sub r with respect to time, plus the derivative of the magnitude with respect to time times the velocity vector. So you end up, when you look at changes in acceleration, you end up with two components. One component involves the rate of change of its magnitude, and the other involves the rate of change of its direction. And for example, if you had curvilinear motion, or what we call uniform acceleration, that is, say you have a rock on a string and you're spinning it around over your head, and it has a constant radial vector radius out, because the length of the rope holding the rock does not change. It's a constant length. And this thing is rotating with some angular velocity, omega, so many radians per second, or degrees per second, or revolutions per second. The change, the tangential velocity, remains constant. This is omega r, revolutions per second times the radial distance out. And this remains fixed for all time in what we call uniform circular motion. This tangential velocity that the object is going around the circumference of that circle it traces out remains constant for all time. So this portion goes to 0. The rate of change of the magnitude of the velocity with respect to time goes to 0, but this component does not, because the direction of the position vector going from the center of the circle to the rock changes. In one case, the position vector is out this way. Another instant of time, it's pointing in that direction. Another one, it's pointing that direction. This position vector keeps track of the position of the rock as it goes around the circle. So its position is changing with time. And that's what this is telling us right here. So this is non-zero. This does not go to 0. So there is an acceleration, even though the tangential velocity, or the velocity with which that rock whips around over our head as we spin it, its velocity magnitude remains constant, its position is changing. Hence, there's an acceleration associated with that change of direction. And that gives rise to what we call the centripetal acceleration, which is directed inward towards the center of the circle. It has the same value. There's a centripetal force that's directed inward as the rock is moving around. There's a centripetal acceleration, I'll call it AC, directed towards the center of the circle. And then there's a centripetal force. The centripetal force is just F equals ma, the mass of the rock, let's say mass of the rock, times the centripetal acceleration. Well, that force, that centripetal force, just happens to be the same as the tension in the rope. That as you're spinning that rock around, there's a tension in that rope caused by the rock changing its direction all the time. And that tension in the rope, that force in the tension in the rope is the same as the centripetal force. Let's see. Over the top of the camera. I didn't think I was going over the top. I'll try to watch out for that. Okay, I'm just going to take a quick break here and then do one little bit and wrap it up for the night and address all the other issues another time having to do with buoyancy, neutral buoyancy, and that. I've got to go off and do something with a friend here. I'll be back in a minute. I'm going to show you something that I'm working on. Has to do with the weight of an hourglass when you tip it and let the sand pour. Oh gosh. Oh, man. That's liquid for the whiteboard to erase. It really affects me. It's supposed to be biodegradable. It's nasty stuff in my throat. Oh gosh. Okay. What this involves, the weight of an hourglass. There was a problem posed in a Hangout a few weeks ago where the question was asked, if you have an hourglass and you put it on a scale and weigh it, and then you flip it over to let the sand pour down from the top bulb to the bottom bulb. The question is what is the weight of the hourglass as the sand is pouring down? Does the weight remain the same as when it was before you tipped it? Is the weight greater because of the sand pouring and the kinetic energy of the sand hitting the bottom and with the momentum imparting a force? Does that increase the weight? Or is the weight less than the static weight of the hourglass before you flipped it over? My answer to that initially when I heard that is I said, the weight won't change. And everybody jumped on me that I was stupid, that isn't the case, that it should weigh more. Well, I went through a mathematical analysis of it, and I'm not going to tell you the result today. I will cover that in a video and Hangout to follow later this week. But to verify my mathematics, what I've done is I'm making this hourglass. These are two champagne glasses that I've glued together with a 1/8 inch hole, and I have dry sand that I'm going to be putting in here. The amount of dry sand that fills this makes this hourglass as a timer for 5 minutes. It takes for the sand to pour through. And the question here, I'll give this for you to think about. If you have an hourglass, let's say here's our hourglass, it necks down like this, and it's sitting on a scale. So initially, your sand is here at the bottom, okay? And you weigh the hourglass. So let's call this weight 1. Now, you flip the hourglass over. The weight, the sand is up here, and now it's starting to pour down. Now, we can analyze this by, let's just say, let's look at weight versus time. So we start off here with a static weight, W1, where we initially weighed the hourglass. Now, I'll give you some hints here to think about. You flip the hourglass over, you let the weight, you open up the neck and let the sand start falling. So what's going to happen? As the sand is falling, before the initial grains hit the bottom of the hourglass, what's happening? The top has lost some mass. So it's losing weight with this amount of sand that's in free flight before it hits the ground, before it hits the bottom of the hourglass. This amount of weight in this sand now is weight that is no longer registered by the scale because it's not attached to the hourglass. So we would expect initially what's going to happen, we'll have a little impulse. The minute we open that up, and as the sand falls down at a constant rate, there'll be a linear decrease in its weight. And let's say at time equals T2, the first grains hit the bottom of the hourglass. So the question is, what happens at this point? Now, there's a couple things you can say. Is one, the grains of sand gain velocity as they're falling down, and they're gaining momentum and kinetic energy. There's some potential energy. When we flipped it over, the sand up here has more potential energy than it did down here. And now the sand is falling. It's gaining kinetic energy. So what happens when it hits the scale? It's got kinetic energy. It has momentum. It's going to impart a force on the scale. So the scale, if you had a total inelastic collision, that is, none of the sand bounces up or recoils. If it just gets absorbed like going into plum pudding or something, then you would expect there to be a spike up. But in real life, you will find that the sand splatters as it hits. This is not a total inelastic collision. There's some elasticity in this collision that's going to get dissipated in heat. And as the sand starts piling up, some of this sand is going to absorb the other sand that's falling on top of it. Some of the sand will get deflected off. So the question is what is the dynamics of that? Does it even out? The weight that's lost due to the sand that's falling, is it counteracted exactly or not by the amount of force? And then once it hits, of course, once you're in a steady state and you have a steady stream, any delta mass loss here is gained down here. So those balance out. So the question is does the force of impact, is that adding to the mass or to the force registered by the scale? Is it compensated by the amount of mass that's in free flight here that hasn't hit down yet? Does all this balance out or not? And I have equations that I've derived that show what happens, and I think some of it will surprise you. But something to think about here is, what does this weight versus time look like? Now, is this thing going to jump up and come to the initial weight, and while the sand is pouring, it's going to be in steady state? So the question is the steady state the same as the initial weight? Is it up above or is it below? And then once we get, say, once the sand runs out, we can easily see that the mass of the sand that was in free flight is now going to start piling up, and we should get a jump up in the weight depending upon where it is here. And then finally, once it all settles down, the sand is poured out, no longer pouring, we'll be at the initial weight again. So the question is what's happening between T2 and, say, T3 when all the sand is poured out? What does this graph look like for weight versus time? And to answer that, like I said, is I'm working on an experiment to verify my equations. And I showed you that 1 hourglass. Oh, shoot. And I have another hourglass that I'm going to be using for the experiment. And what this is I have a top bulb here. And when I pull the plug out, the sand will fall down. So this can sit on a scale. And we pull the plug and we look at, see what happens to the weight on the scale. Now, there's a couple things that can impact this, of course, is the distance that the sand falls that would determine how much momentum or kinetic energy it gains. So I have the ability to move this top bulb up and down to test at various heights whether or not or how it impacts the weight on the scale. And there's a certain flow rate that I have with this particular sand, and I'll be using this to test my equations, my analysis, to see if my analysis agrees with reality. So the question that you can work on here is how to complete this graph. Complete this graph. Does the weight of the hourglass as the sand is pouring increase, decrease, or remain the same as the initial weight before you flipped it over and let the sand pour down? And like I said, I'll be doing this by the end of the week. I should have the hourglasses complete and the video done showing how it indeed behaves. So I'm going to wrap it up. Oh yeah, also I'll show you here is I've got a little spring scale that I've been making. Let's see if you can focus in here. I have it calibrated in grams, and this will be used for another experiment. I was doing this to determine spring constant K by attaching various weights on here. For example, if I have I've got some calibrated masses for my scales. This is a 200-gram weight, and you can see it's right at the 200. And I did this for in 50-gram steps to 350 grams. And if you see, as you can see, all springs have a linear range. That is, the characteristics of the force on a spring is its spring constant times the distance x at which the spring is stretched out. Say you have a spring fixed here. This is its rest position. This is x equals 0. Now, if you stretch this spring out where it goes, you stretch the spring a distance x, the force is directly proportional in its linear range. You double the stretch, the distance, it takes twice the force. And as you can see, when I calibrated this, how it always ends up is indeed we see a linear step going here. We've got 100, 150, 200, 250, 300, 350, and these are equal size steps. So this spring acts in a linear range from 100 to 350. Of course, you can imagine if you put a real heavy weight on this, that eventually the spring will deform, it'll get stretched out and not go back. But there is a range over which all springs will act linearly in this manner. And by calibrating with the weights, I can determine the spring constant K by attaching various masses, because the force on the spring is equal to the weight of the mass, and the weight of the mass is mg, knowing the gravitational acceleration here on the surface of the Earth. You can calibrate the spring and determine the spring constant by attaching various masses and measuring how much the spring stretches. So that's all going to be part of the ongoing tests and experiments that I'll be talking about in the future. So anyway, I'll close it down for now and talk a little bit more about forces next time, and then get into neutral buoyancy and more on buoyancy. And then eventually I'll be talking about the Earth's atmosphere, its makeup, and how to calculate the buoyancy, say, of a helium balloon. Given a certain volume of a helium balloon, how much buoyant force it will have, how much it will lift given a certain volume. I'll show you how to do that. And I also have some helium balloons that we can test. We can determine the buoyant force for a given volume of helium, and then we'll compare it to the derived equations that I come up with. So good luck all, and till next time. Okay.